Wednesday, June 14th, 2023, Seattle, Washington. Yeah, I've been studying the complex variables from this great book, Functions of a Complex Variable, Complex Analysis. And what was established in the first couple chapters of this book was notations and conventions about the definitions of the existence of a square root of a negative number, in this particular case, -1, about the roots of unity that might so exist in this complex plane. One might imagine another way to think about that the product of two numbers is 1. They're not roots, which is that a constant taken to a power is the number, but they're factors or multiplicands, arguments to operations that so result one, like the hyperbola 1 over x, x times 1 over x equals 1, and these kinds of things. Vis-a-vis what's been discussed here is this identity dimension and about the reciprocal function or inverse or the hyperbola in the positive numbers quadrant of the Cartesian, and about how that establishes its own kind of coordinate setting about the origin and the half plane as about it geometrically. There's a usual general geometrical attachment to anything because it reflects what's A, according to vision and perspective and projection, and B, what can be diagrammed or drawn on a flat piece of paper or the sand, or otherwise a geometric surface in 2 dimensions. Vis-a-vis that 1 dimension is only space enough to write, say, a code or an array of dashes and dots or something, and then in terms of whether that admits a measure, and instead of that there's always another dimension relative to it that emits a measure, is a thing to consider, which is one reason why when they think about the hologram, the idea of the hologram is that all 3 space dimensions naturally wrap up each other in terms of how they twist together, making up 1 dimension naturally, that the hologram is 1-dimensional. And the idea is that somehow is encoded in it higher dimensions. And so then that gets into why, as the numerical resources of the entire setting, why 3 space dimensions is enough for all of space-time, and then that the time is considered usually a 4th parameter or variable or dimension. It's kind of a ray of time, though, not so much back and forth. The x, y, z dimensions, or e1, e2, e3, according to the orthonormal vector basis, e1, e2, e3, or r cubed, the real numbers, positive and negative. Geometrically, those are the most usual milieu and encode everything in terms of space and location, or displacement from an origin or a fixed point. So the hologram is the idea of how to encode that in less, and like what's that's projected into, and it's almost kind of like the point at infinity, this kind of thing. All the contents of the space-time, the rest of the objects of the physics, of course, describe in all their individual pieces and parts their own sorts dimensions, their own sorts coordinate settings, their own sorts numerical resources, their own sorts content, while at the same time the idea of the fundamental theory of unified field theory of physics has that they are all defined by fundamentally 1 equation. It's parameterized by time. It's a dynamical system. And so in this sense, that's inclusive and universal, but not tractable. And so then any sort of application usually just reduces that to parts, and then treats the parts constructively and classically, and then applies to them all these various models that go into the models of motion, where motion and uniform motion or constant velocity is one thing, and rest or relative location at any given time is the other thing. And then all the dynamics of acceleration, which is described here in terms of the usual notions of the higher order derivatives of velocity and changes in velocity. dv dt is acceleration. And there's also the derivative of stopping when you get to thinking about acceleration and deceleration and parting and meeting, and in terms of that velocity is a constant parting from the origin and meeting of the destination. So then when that's considered with respect to rest, is that everything else is in motion relative to that rest. So the idea of that, it gets into how to express in what's kind of the inverse order of that. Deceleration is still just dv dt where it's negative. But at the same time, it can be considered dt dv, another way to look at it. Kind of like there's this deconstructive arithmetic about addition and division, it's complements. So take them apart, then until they add up in the middle, it's not complete arithmetic. And indeed, the way everybody learns it is that it eventually follows at the end the one for the other. And then the completeness is so defined, and that's the central classic character of arithmetic. And the numbers, the objects of the numbers, essentially defines a lot of their properties. Here the idea is the way to look at that is in terms of then that dt over dv would be in these powers in orders that are negative, instead of that the quantity is negative. And so there's kind of like positive acceleration and positive deceleration, instead of positive acceleration and negative acceleration. Why contrive such a hump to get over, to put together in the formalization such a thing? Well, the idea is that it naturally adds up. It's the extra classical bit that makes it possible to get things to add up. And so what was looked at is kind of these ideas that in our realm of differentiable functions, C infinity, the infinitely differentiable functions, they can be differentiated infinitely many times. They're continuous functions mostly. And so it arrives at then for polynomials or power series, that goes to 0. Because anytime you take the derivative of a power, it reduces its order or rank by 1 till it gets to 0, at which point in time it's forever after 0. It's kind of like the identity in terms of the additive identity or multiplicative identity. The additive identity is 0 and the multiplicative identity is 1. But the multiplicative annihilator is also 0. So with regards to the completion and closure of those various things, you have the C infinity functions coming down, and then the idea is to figure out what that means when you just reverse the order of the integration in terms of these relative quantities and this and that and the other, to make it so that then the idea is to figure out what's the quantities that make it so when you start, because when you take the antiderivative of the inverse, x to the negative 1, it becomes like ln x, the natural log of x. And then as you continue integrating that, it comes up and actually just gets into this ever-expanding function that comes out. Where when you take the antiderivative of x to the negative 9, it becomes x to the negative 8 and x to the negative 7 and dot, 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 disregarding constants, which fall out according to the power law of integral calculus. that gets into what's to be determined is the quantities of that function that ends up being the infinitely many antiderivatives or pre-derivatives of x to the negative 1 over x, how that arrives at 0. That's the sort of complementary dual that makes for why, when you think about the infinitely many higher orders of acceleration, they basically start at 0. And meaning that to change from rest to motion at all is all the higher orders of acceleration. Infinitely many. So the idea is to figure out how that works out for this different derivative stopping. And then that's just kind of a relation to, like, time to 0 to 60 versus stopping distance, these kinds of things. That ends up being for what would have its own model of just by itself, acceleration and deceleration and parting rest. So coming back from that, coming back into that these are still the same dimensions in space and time, although you really only need to consider a array of time and a direction of time. And then when everything is universally parameterized by time, it's back to just 3 space dimensions and its contents and the tendencies and propensities of the objects in space-time by the principle of least action and least surprise. They just do what they do. That sufficiently higher organized systems, like things that analyze and use theories of intelligence, can make decisions about when to strike when the iron is hot, to take advantage of a global minimum or maximum, to shift something, and thus that it results that when it falls back according to its natural potential, that it would be displaced to to push something. These are just usual relative notions of how to try and figure that out. That it becomes a lot about this rolling back up into the hyperbola and the inverse, and then the identity dimension, how to make for so that that's better understood, that the integral of 1 over x is ln x, and then the integral of that is ln x minus x, and about how that gets into x minus 1, and these kinds of things, in terms of making that a function that results, then it comes down as this complement, and then it solves the dt over dx for the dx over dt, or in sufficiently that it has the form for each of those higher orders of acceleration, that it makes for the complement of the usual linear inputs, force equals mass times acceleration, to get force equals acceleration times mass. That those quantities end up being the same quantities, but they're derived from either side. Newton's 0th laws of motion and acceleration and deceleration. So in these complex variables, coming back to that a little bit more closely, then there's built up the definitions about what the arithmetic products of these objects are. So when you think of something like a computer language or any kind of arithmetic, the idea is that quantities and terms, these values, are related by these operators, which are familiar as plus, minus, multiply, divide. With very particular quantitative properties about the operations of algebraist field, or that the difference between products that are a sum and products that are let's call the product, the multiplication end up maintaining the ratio and form of proportion for these operations. The operators are defined. And so the idea is for the complex numbers is that the operators are defined. The objects, by their values, each of value, is equipped with operations that define pairwise for any pair of values what is the result of their operation as an object of the same type. Now, a lot of discussion here before is about the inner products and outer products, that this is just a product. And an inner product is something that usually reduces the dimension, makes a scalar. An outer product is something that kind of takes both sides, the bivector, four-vector, these kinds of things. So for this complex analysis, for the complex numbers, there's established what would be their properties of addition, subtraction, multiplication, and division. And the only really funny one there is kind of like is division. Because otherwise it's just kind of pairwise by monomials of rank and order 1 that it's well, I guess it'd be multinomials because it's x plus yi, that those are just pairwise themselves in terms. But then for division, it ends up looking like the linear fractional equation. Two linear functions, fx equals mx plus b over gx equals nx plus c. Then when you think about the division, what defines the complex numbers, it emits this whole line of thinking about singularity and multiplicity that this whole identity dimension bit has brought to the linear fractional equation and the linear fractional transform. So anyways, that's the operator overloading, we'd call it in programming, or providing so that in the syntax of the language you can write expressions into terms of the language by the variables and the constants with these operators, and then they establish that the operations are defined by how they're equipped, or the overloads, the operators defining the functions or relations that so follows from the operators. Relations are Boolean valued, and functions are of given types, say. And functions that are whose inputs and outputs are the same type or a particular kind of function, and that's something to be figured out. Monadic function, monary, monotype functions. So anyways, it's to be figured that that's multi-valued. Division generally in complex numbers is like division by zero. Well, why is that? Well, it's because the whole identity dimension bit works it up, paras that out, that when you try to analyze that as about Claro and D'Alembert and the linear fractional equations, all of which I've been learning about from these university mathematical texts, stack of them, little stack, has that it's special. And so at the same time, what convention is picked about it is fixed, that it's also free. So it's a foothold, a toehold to scale the edifice to get above what where it can be found, otherwise what it could be. So anyways, that seems the first point where the operations equipping the objects of complex analysis are having analytical multiplicity about singularity theory. These things are called singularities and closed, but because they're multiplicities that are open. And then it shows about various laws of the properties of the products of the operations according to the precedence and the priority of the operations that usually you divide and multiply or having higher precedence and priority, then add and subtract. But parenthetical groupings define for the expressions, which are the quantities that are evaluated first, and it's evaluated from the inside out, and then otherwise left to right. That the entire point of parentheses is anything different from left to right. We easily see that the fundamental laws of algebra are all satisfied. So here, there's carefully delineated what are the same things for arithmetic and algebra, and what are not. And so, that they happen to come together in the middle is a great thing, but they can be put together various ways, which is relevant and a thing. But again, in this framework of the declaration of these things, these objects for the continuing chapters, it'll hold like so. Commutative and associative laws hold for addition, multiplication. The distributive law of the field holds. One property of the real numbers is trichotomy, meaning the three cuts, meaning that any two numbers, x and y, either x is less than y, x equals y, or x greater than y. As the author notes here, just kind of scanning what we already read, complex numbers do not have such thing. But of course, their terms do in the x and the y, and then they do in the r and the theta in terms of the polar notation. Which is also different because polar notation is not unique, because any multiple of 2 pi can be added to the theta and it's the same value in the plane. If you consider that every time theta goes around, it also traces 1 unit deep into the plane, into the z dimension. You can readily establish that makes for regular depth. And so the second thing that came into the definition was for the definition of division. Well, here it says definition of division. Consider the equation, and I need to refresh my familiarity with the Greek letters, because there's upper and lower case, and sometimes I'm just not sure which one is which. That z. Is that gamma? Is it eta? Is it epsilon? It's not epsilon. I'll look it up later. And there are various forms of the lowercase ones too. Z zeta equals z prime, where z equals xy. Zeta equals epsilon nu. I'm calling that nu. Z prime equals x prime y prime. Then we have that x epsilon minus y nu, comma x nu plus y epsilon equals x prime y prime. So this is to divide that z times zeta equals z prime. And then to define what is z as z prime over zeta is what's going to be tried to be figured out here. Then we have x epsilon minus y nu, comma x nu plus y epsilon equals x prime y prime. So it's multiplied them together, the one side, so that x epsilon minus y nu equals x prime, and x nu plus y epsilon equals y prime. So pairwise, each one is just related to the corresponding related factor. And on solving for epsilon and eta, epsilon equals y prime plus x prime over x squared plus y squared, and nu equals xy prime minus x prime y over x squared plus y squared, provided that modulus magnitude of z is not equal to 0. Hence, if modulus magnitude of z is not equal to 0, there is a unique solution, and zeta equals epsilon nu is the quotient z prime over z. So now this has this attachment to the coordinates, and it's something I'm going to be looking at some more. And it's one of these things that sticks out in the analysis as that x squared plus y squared cannot be 0, in as to whether you can consider a complex number in the complex numbers. What do you mean a complex number in the complex numbers? Well, what if you think about x and y as a plus bi, x plus yi, as not just x and y in the real numbers, but what about the world where they can be complex numbers or imaginary themselves? What if you have it like this? So then this x squared plus y squared, which in the real numbers is only 0 when x and y are identically 0, because x squared and y squared are each positive if x and y are positive, or one of them is positive if either of them is positive. In fact, one of them is positive if either of them is non-zero, because x squared is always positive from real numbers. But what if you think of a complex numbers? That would probably be my approach to figure out what would be other ways to look at that, and then figure out that otherwise these are complex numbers. I added another dimension. I said that the coefficients could be complex again themselves, and then what is to be followed out is that these other properties still hold up because it's just still pairwise in arithmetic, and then that some of these other derivations make it so that there's more conditions where that it would be singularities and multiplicities. And what I'm pointing out then is as how to break it open, because then I'm going to associate that kind of multiplicity with this identity dimension about the linear fractional equation, because the linear fractional equation is what these look like with returns to these quotients of each other. That besides solving for the product, one of the terms in terms of the other, according to arithmetic and the arithmetic of the terms pairwise, it's going to be in terms of these complex numbers. So yeah, after yesterday, when I'm reading about the complex numbers and trying to look into de Moivre's theorem, because then it becomes pretty much important in terms of Euler's theorem and then Gauss's entire integral analysis and this and that. This is the kind I'm looking for to make it so that to go the roundabout way, then it ends up being a second higher order but simple thing back on the positive numbers. And so that's the idea I just had from trying to figure this out. Now, my mind attacked it to find its weakness and break it open and to show its true inner side. Turned it over. And now turning it back over, of course, is still the same. The mathematical object is not hurt when you attack it. It's just work on it. So that seems kind of a nice thing. I gave it a defense. A mathematical defense is a proof. You give something a mathematical defense, and then it constantly, continuously defends itself forever. That's the great thing about mathematics. It stands up for itself if you treat it right. So then we already read this. So we were looking at the definition of division is contrived and contrivable, and an outer product in a greater field to be established that the complex numbers have properties of usual algebras, or that they have them in various areas. We'll get back into that in a while. It is customary to denote a complex number whose imaginary part is 0 by the real number symbol x. So one of these complex numbers would look like so. When using the abbreviated notation, conjugate. Then there was the conjugate complex numbers. So the conjugate complex numbers make it so that because they result that one of the terms in the computation of their expansion, which is multiplying them together, and then you have all the terms in their various orders according to the powers in algebra and the terms and the ranks and the orders. And then in the middle would be the cross term that's a product of either side, and it's the lower order on either side. And then the idea is this conjugate is that because I squared is -1, and the one term that otherwise would be the term of the second higher order, that just cancels itself out. It's no longer imaginary because this square is the square of I is 1, and then there's this assignment of it to being a real number again, and then all the derivations is where it sits in the middle. So instead of kind of like this notions of the non-standard analysis and the completions for the deductive analysis is the inductive impasse, the middle of nowhere, and the meeting in the middle. This kind of analysis, the usual deductive analysis about the origin and everything comes back, comes back to the middle and comes back to the origin, is a similar kind of thing. So these conjugates are the second point of attack on the complex analysis to make it so that then when there's a model of this, and this was just framed kind of in the identity dimension. So the idea is these complex numbers, like the linear fractional equation, have a singularity in the identity dimension. Conjugates on that are going to be defined. Make it so to make for more ways to assign addition formulas, relations, and identities in complex numbers, ... that are as real as the usual ones. Because after de Moivre, we get into Euler's famous theorem. It's like, wow, Euler was one of the most famous mathematicians and considered one of the greats. And out of all that, he's got one formula that's really named for him, and it's called Euler's formula in the complex analysis. It's like, well, that's pretty great. Of course, E, the constant natural logarithm, is said to be named for Euler as well, but or Euler. But the point is that the branch of analysis is going to follow from that, as that's being kind of a center, but there is the surrounds, and what we're interested in is the surrounds. Then there was the geometrical representation that says, well, so now we defined an Argand diagram as this complex plane, and also we're going to treat it the same coordinates as the real coordinates, and we're going to draw regular geometrical shapes in them, like a rectangle. And then we're going to use that to compute these angles, and then we're going to talk about how the angles have like this representation, and then that gets into de Moivre's theorem. And courtesy, cosine theta, I sine theta. Well, what's cosine theta, I sine theta? Now they kind of leave that out of the derivation in this part of the book, and I wish it was kind of here what course they had taken, because there's lots of identities in the cosine and sine and addition formulas and about their powers. And a lot of it has to do how it can be reduced to that they're orthogonal functions. And so what I'd be curious of, because in the best known of these that I know is cosine squared theta plus sine squared theta equals 1, which is like cosine theta squared, sine theta squared. So I sine theta squared is negative sine squared theta. So the idea is to figure out why that results this subtraction formula. And so for that, what I'm going to be studying kind of later, or at some point, is a refresher on the identities of trigonometric functions and things like half-angle functions, squares, relations to the hyperbolic, usually relations to the Pythagorean, and relations as orthogonal functions, and about small angle approximation, or where identities in this can be formulated in terms of L'Hopital's rule, about that, and otherwise to figure out why it's made so that then for this Argand diagram that it makes up for de Moivre's theorem. Because de Moivre's theorem then says that the product of the z's of all these different complex numbers equals the product of the r's, and the product of the cis's that's of the sum of product of it's the product of the z's equals the product of the r's times the cosine plus I sine theta of the sum of the thetas. And as the wiki put it, and when I'm curious and want to learn about something, I turn to the Wikipedia, the online encyclopedia, and it's generally reliable and pretty well filled out. And especially since the last 15 or 20 years, it's gotten a lot better than when it was just initially populated by people usually with their axe to grind, or their shill to sell, but by now it's most of the things have been gone over well enough that it's pretty balanced and conservative in what it offers. Yeah, rather full, and with particular sections in this that all these different fields in the descriptive differential dynamics all have Wikipedia pages, and it's kind of a natural result of fields wanting to keep themselves relevant. A lot of people turn to it. So when I want to figure out that cosine theta plus I sine theta is a thing, and about what I would look to refer to in the trigonometric identities and these kinds of things, that's where I went and studied a bit about de Moivre's theorem. And so what it said was, it's like de Moivre's theorem is what relates the complex numbers to the trigonometric functions. I'm like, okay, but what I'm curious is to relate the complex numbers and these complex numbers to trigonometric functions and orthogonal functions. They don't have that yet. It's a thing. It's like yesterday I was looking up the fundamental theorem of algebra, which is like a polynomial of rank n has n roots. But these days somebody has gone and painted all over the top header, but it's like, this is all a theorem in complex analysis about how it comes down in this in our complex analysis. I'm like, that's totally opinionated. That should be at the bottom of the page or somewhere in a little subsection, not like after the first thing about fundamental theory of analysis. It's like somebody went to the fundamental theorem of arithmetic, which is like integers have unique prime factorizations. And on top of it, put it in something like algebraic geometry has a Dirichlet universe, or excuse me, not a Grothendieck universe. And how we talk about it is all this second order, higher order logic stuff that makes it so that there's no way to look at it except come down. It's like, no, that's misplaced centrality. Anyways, someone might change that tomorrow. Anyone can sign up and log into Wikipedia and suggest and make edits in any of the Wikipedia pages. So de Moivre's theorem is where we got, and then the idea is to figure out then what that's going to mean for analysis. So coming forward, now we've got up to, that's where we read up to was, since the absolute value of I, or the magnitude of I equals 1, multiplying by I leaves x plus yi unaltered. So that would be similar for these complex numbers. It's like triangle inequality. It's like triangle double inequality, or something like that. double triangle equality. Set of points in the Argand diagram, section 4. Chapter 1, section 4. Set of points in the Argand diagram. We now explain some of the terminology necessary for dealing with sets of complex numbers in the Argand excuse me, in the Argand diagram. To my health. Bless me. We shall use such terms as domain, contour, inside and outside of a closed contour, without more precise definition than geometrical intuition requires. The general study of such questions as the precise determination of the inside and outside of a closed contour is not so easy as our intuitions might lead us to expect. For further information, see e.g. DNA's The Taylor Series, Oxford, 1931, Chapter 6. In dynamical modeling and in these series of in the integral equations for plane curves, those are called the level lines, so from the one perspective or the other, it's intractable. It's an impasse. It's the inductive impasse and this kind of thing. And so when the one field in geometrical intuition is where it's built, it's like I get what's inside because if you have a closed curve on a plane, then almost everything is outside of it. And what's inside basically has that it will necessarily have it that any two lines that reach across a circle will intersect each other, whereas all the lines on the outside will never necessarily intersect inside the region, meaning that there's ways to think of what properties would make it so that for the fields of lines they're in, or the level lines, there's ways to find inside and outside. And it's intuitive, and it's one way to look at it, but as the author puts forward, it's necessary to establish this whole sort of complementary duals to figure out a way to make sure that the transfer of results about the one or the other in the way that it's sensible, functional, and tractable is both tractable and then sensible in the one or the other. For our present purpose, however, we shall find that no difficulties arise from our relying upon geometrical intuition. Well, there's only a few pages to get to. By a neighborhood of a point z0 in the Argand diagram, we mean the set of all points z such that z minus z0 is less than epsilon, where epsilon is a given positive number, and that's the magnitude of z minus z0. So according to before, I was just described how there's a distance and measure and this and that in terms of analyticity and complex numbers and their coexistence with points on the R2, the real plane, and their magnitude, and about the distance, the metric, the norm, and the triangle inequality, that such delta epsilonics are built up and established about that. Epsilon is an arbitrarily small quantity. He says a point z0 is said to be a limit point. So this is topologies. These belong to the field of topology, usually, of a set of points S if every neighborhood of z0 contains a point of S other than z0. Definition implies that every neighborhood of a limit point z0 contains an infinite number of points of S. And furthermore, every point in every z0 is a limit point. For the neighborhood 4, the neighborhood contains a point z1 of S distinct from z0. The neighborhood of z minus z0 is less than z1 minus z0. contains a point z2 of s distinct from z0, and so on indefinitely. This is delta epsilon x. In the complete ordered field, where the halving or splitting or dividing any positive real quantity still results a positive real quantity. This is the standard analysis, not the non-standard analysis where after the sortes and heap that it becomes infinitesimals and zero. It's nilpotent or nil square and this kind of thing. 4 ... that establishes that we've gone from this these numbers and that their closures make it so that then it's like so based on the properties of real numbers, because the magnitudes are like so and this magnitude is like so. So he's defined an establishment of what's a limit point in a neighborhood. The limit points of a set are not necessarily points of the set. If, however, every limit point of the set belongs to the set, we say that the set is closed. There are two types of limit points: interior points and boundary points. A limit point z0 of S is an interior point if there exists a neighborhood of z0 which consists entirely of points of S. A limit point which is not an interior point is a boundary point. A set which consists entirely of interior points is said to be an open set. So this closed and open are not antonyms. They're not. It's not a binary property where the antonyms reflect Boolean. The negation of one is the affirmation of the other, and vice versa. So it's open and closed about. Then there's a term in the middle called clopen, C-L-O-P-E-N, clopen. Here the author says, it should be observed that a set need not be either open or closed. An example of such a set is that consisting of the point z equals 1 and all the points for which mag z equals less than 1. Now he says, we now define Jordan curve. So Jordan, here from these discussions, has been about the Jordan content or Jordan measure, and the line elements and what it takes for line continuity to establish a measure for Jordan content and Jordan measure. But here it's about his curve. We now define a Jordan curve. The equation z equals xt plus iyt, where xt and yt are real continuous functions of the real variable t, defining the range alpha less than equal to t less than equal to beta, determines a set of points in the Argand diagram, which is called a continuous arc. A point z1 is a multiple point of the arc if the equation z1 equals xt plus iyt is satisfied by more than one value of t in the given range. A continuous arc without multiple points is called a Jordan arc. So this would be as of any curve drawn in the real plane, whether or not it crosses. Those crossings are called multiple points. A continuous arc without multiple points is called a Jordan arc. If the points corresponding to the values alpha and beta coincide, the arc, which has only one multiple point, where it'd be like a circle, a double point corresponding to the terminal values alpha and beta of t is called a simple closed Jordan curve. A set of points is said to be bounded if there exists a constant k such that mag z less than or equal to k is satisfied for all points z in the set. No such number k exists, the set is unbounded. And he says a domain is defined as follows. A set of points in the Argand diagram is said to be connex, C-O-N-N-E-X. It is an adjective that is connex if every pair of its points can be joined by a polygonal arc which consists only of points of the set. I think that's supposed to be convex. That's what's convex. So I don't know why, I'm not sure exactly what convex is vis-a-vis convex. But convex and concave reflect basically that if it's swelled out, it's convex, and if it's dented in, it's concave. Okay, like concavity, an open domain is an open convex set of points. So he reuses this term, and it's what it is. Connected or joined by a polygonal arc, which consists only of points of the set. An open domain is an open convex set of points. The set obtained by adding to an open domain its boundary points is called a closed domain. So this is the inside of this simple closed Jordan curve. The Jordan curve theorem states that a simple closed Jordan curve divides the plane into two open domains which have the curve as common boundary. Of these domains, one is bounded and it is called the interior. The other, which is unbounded, is called the exterior. Although the result stated seems quite obvious, the proof is very complicated and difficult. One way to think of it is that, like, the interior surface is only in the plane. Everything else is all the curves from all the higher order planes that go around it. It's like, well, what do you mean, Ross? It's like, well, imagine if you put a disc in a wind tunnel and you visualize all the streamlines of the air flowing around it. So they never cross the disc, but they're everywhere else. It's a still pool, but there's a flow everywhere. When using simple closed Jordan curves consisting of a few straight lines and circular arcs, geometrical intuition makes it obvious which is the interior and which is the exterior domain. Basically, the interior domain is finite and the exterior domain is infinite. For example, the circle mag z equals r divides the Argand diagram into two separated open domains, mag z less than r and mag z greater than r. Of these, the former is the bounded domain, is the interior of the circle, mag z equals r. The latter, which is unbounded, is the exterior of the circle, mag z equals r. In complex variable theory, we complete the complex plane by adding a single point at infinity. Whoa. This point is defined to be the point corresponding to the origin by the transformation z prime equals 1 over z. Now recall, we were just talking about the definition of the hyperbola and the multiplicative identity 1 and the multiplicative annihilator 0, and we were just talking about the complex numbers and the complex numbers and the analysis about the identity dimension, about the definition and division of complex numbers. So the author of that says there's a point at an infinity, and this is usually what we call the projective point at infinity, and that's just like when you diagram x and y, then for x all the way to the right is a point at infinity out there, and for y all the way above is a point at infinity out there that's arbitrarily large. And when we think about like an arbitrarily large number, that 1 over that number is arbitrarily small, like 0. about 1 over 0 equals infinity, or 1 over infinity equals 0, or 0 times infinity equals 1. Undefined, indeterminate forms, singularities exist in the abstract, but the operations don't hold, except it's so contrived about this points one or the other. So the author just kind of tacking this at the end of the section is in this language. This point is defined to be the point corresponding to the origin by the transformation of z prime equals 1 over z. So the origin is it's defining an inverse for what's 0, because you know it's like, because arc z of the origin, or 0, mag z. So anyways, this is very incongruous paragraph here, but it reflects the same thing as 0 times infinity equals 1, or 0 equals 1 over infinity. Not so different. That's his definition of infinity. Section 5, functions of a complex variable continuity. We've read a section there, say, and I do endure a bunch of my comment about notation and the edifice, and figuring out how to establish where the sidewalk ends, the definition ends, and where it's possible to figure out how to provide supplementary definitions or complementary definitions that make up for a complement that in a fuller whole, a bigger picture, still has all what results from the original definitions and their completions and their limits and all that what holds. And then as well, from up above, or the other side, comes back and then has its own limits and completions that they meet in the middle, which to either of them otherwise is the middle of nowhere and beyond the flat Earth, where the sidewalk ends. That's kind of the idea. So the point of looking at this function as a complex variable is to establish what would be the 20th century's working terms. So that then when we look at that after it's been kind of spindled, folded, mutilated, or washed, spun, and dried, or however you so care to put it, for new math, and then algebraic geometry, algebraic geometry, or this or that, is to establish, similarly in this course for the differential, where the idea is to figure out what it means in terms of plane curves and integral equations, and this complement differential equations and their solutions, when it's really the one defines the family, the other defines the family of it. Then to similarly here with these complex numbers, just to see that these are the definitions of the complex in argan, they're still in effect. But you'll find various things that will be like left off, or it'll be interesting to see if there's other contrivances where they say, we figured out another way to shortcut the definition of the conjugate or the definition of division, so it's cut in or cut out, or we're not going to talk about continuous things or the boundaries or topology because that's all left out. It's going to vary, it's going to depend, and it's going to differ in different subfields, and that's fine. But the idea is to establish and refresh, and kind of after having internalized long ago what was the experience of this exposure to these concepts and ideas, in the rush and in the flood of all the things that are going on in the linear curriculum, and to get up to where these things are coming together. So, for example, in this functions of a complex variable and complex analysis, you expect kind of the later sections of these chapters to get into like particular things to do with like this is an example of a derivation which makes sensible an application somewhere else, and it's a funny little corner case or something. And then other times it's like, well, the section will be about, well, this is an entire introduction to a different subfield, but it'll be relevant because then we're just going to place results in it, or vice versa. But what he gets into is functions of a complex variable, and these are going to be discussed and considered pretty generally. And then conformal mapping, rational functions, hyperbolic sine, functions of sine and hyperbolic cosine, and vice versa. Logarithmic function, and some, as he puts it, important relations and identities. Many-valued functions. This is really a key concept, is the many-valued function or multi-valued function, because almost all these things to do with the whole existence of the square root of -1 is that root as a many-valued function. In the definition of a regular function, we note that a regular function must be one-valued or uniform. Quite a number of elementary functions, such as z to the a not an integer, log z, arc sine z, are many-valued. Here there's going to be a general consideration of the complex numbers, and which ones of those are still single-valued as strong, and which of those are more multi-valued is also strong, and making inner and outer products about them. Branches and principles, and this and that, and thus and thithers. Conformal representations, this is the affine, this is the transformations, this is what enables the application and treatment of algebraic geometry writ large to lots of different things. And also then in terms of the analysis, in terms of metrics and tensors. Not so much about complex analysis. This is just like, well, here's how complex analysis fits in that, which belongs to geometry. Geometrical inversion, inverses, transformation inverses. Coaxial circles, arg z minus b over z minus a equals a p hat b. What? If the principal value of the argument be chosen. It follows that if theta is real, a tilde equals gamma e to the I theta, so w equals z minus a over a tilde z minus 1 ei theta. Well, see, now I've been looking for something to do about this derivative stopping I was just talking about. So now I'm curious about the Mobius transformation, which transforms the unit circle arg z, or mag z less than equal to 1 into the unit circle mag w less than equal to 1, where w is defined quite earlier in the land of the Mobius transformation. Yeah, that'll be interesting. Well, all right. This book has quite a lot in it, and it's very condensed. I didn't really care for complex analysis, but now that I have quite a varied and wide body of knowledge in most other fields of analysis, and I'm very familiar and comfortable with function theory and type theory and the arithmetic and algebra and topology and geometry and set theory and the foundations and this and that. And I've always been interested in, after the complex numbers like the quaternions, the hyper complex numbers, and anything to do after, besides, you know, the real numbers, of course, and the infinite dimensional vector space of the real numbers in the Euclidean, and what it means in terms of the argand here and this and that. It'll be interesting. It'll be interesting, I think, to figure out how to get above that, and to figure out how there's a middle, and that there's complex numbers, and to figure out between, if there's going to be real numbers, then there's going to be an identity dimension, and if there's going to be complex numbers, there's going to be complex numbers, and the reals can be their identity dimension. And in this sort of manner, it's going to be possible to work up some various things that help figure out, for Newton's zero-eth laws of motion, how those add up to it's not just a good idea. Hey, well, have a great day.